Two-chip architectures power literally every device you own. One runs your laptop. The other runs your phone. Why do they exist? And which actually wins? It's 1978. Intel releases the 8086 processor. A 16-bit chip with 29,000 transistors. That single chip becomes the seed of every desktop computer for the next 40 years. Intel called this architecture x86. The 86 suffix would echo across generations. 8286, 386, 486, then Pentium. Each chip stayed backward compatible with the original. The design philosophy was simple. Pack more instructions into the chip. Let software do less work. The CPU would handle complex operations directly inside silicon. This approach got a name. CISC. Complex Instruction Set Computing. One instruction could load, calculate, and store memory in a single step. Powerful but expensive in transistor count. Meanwhile, in Cambridge, England, a small company called Acorn was building computers for British schools. The year was 1983. Their needs were different from Intel's. Acorn engineers wanted a simpler chip. Cheaper to make. Easier to design. They studied research from Berkeley and Stanford, and chose a radically different path. They called it the Acorn RISC machine. ARM. Reduced instruction set computing. Fewer instructions. Simpler instructions. Each step did less work, but ran faster and burned less power. By 1985, ARM had a working prototype. The chip drew so little power, engineers thought their voltmeter was broken when they first measured it. Throughout the 1990s, Intel ruled desktops. ARM was tiny. A niche player. But ARM made a bet, licensed the design to anyone willing to pay. Intel built and sold its own chips. ARM never made a single chip. Instead, they sold blueprints. Apple, Samsung, Qualcomm, all could design custom processors using ARM's instruction set. Then 1993 happened. Apple launched the Newton handheld. Inside, an ARM processor. The first mass consumer mobile device. Battery life was the design constraint, not raw speed. 2007. Steve Jobs unveils the iPhone. The processor inside. An ARM design. Suddenly billions of people carry an ARM chip in their pocket every single day. Why ARM for mobile? Power. A laptop x86 chip burns 45 watts. An ARM phone chip uses about 3 watts. The math just works for batteries. But this isn't just about watts and battery life. The deeper difference lives at the instruction level itself. Let me show you what actually happens inside the silicon. An x86 instruction can be variable length. 1 byte. 15 bytes. Anywhere in between. The CPU must figure out where each instruction ends before it can run the next. ARM instructions are always fixed length. 4 bytes exactly. The decoder always knows precisely where the next instruction starts. Simpler decode logic. Less power consumed. More parallelism possible naturally. x86 has hundreds of distinct instructions. Some perform entire complex algorithms in hardware. There's literally an instruction just for calculating cyclic redundancy checks. Powerful, but the chip pays heavily in complexity. ARM keeps it lean. Around 50 core instructions. Want to multiply and add? Write 2 instructions. The compiler does more work, but the hardware stays small and fast. Memory access is another battleground. x86 lets you compute directly from memory in one instruction. ARM forces you to load into a register first, then operate. This sounds slower for ARM, but it isn't. The simpler design means ARM can fit more cores on the same die. More parallel work happening at once. Modern x86 chips have 16, 24, 32 cores. Apple's M-series ARM chips ship with up to 24 cores too. The performance gap has nearly disappeared. Cache hierarchy works similarly in both. Both architectures use L1, L2, and L3 caches. But ARM designs tend to spend less silicon on caching, prioritizing more cores instead. The big.LITTLE design changed everything. ARM pioneered mixing high-performance cores with low-power cores on the same chip. Your phone uses tiny cores when idle, big cores when busy. Intel only adopted this in 2021 with Alder Lake. ARM had been doing it since 2011. 10 years of lead time on power-aware computing. Then came the cloud. Amazon's Graviton processors. Custom ARM chips designed for servers. 40% better price performance than equivalent x86 instances. The cloud started shifting. Microsoft, Google, Oracle, every major hyperscaler now offers ARM-based servers commercially. Workloads that used to demand expensive Intel Xeon chips now happily run on ARM Neoverse cores instead. The mobile world was always ARM. Android phones, iPhones, smartwatches, tablets. Estimates put ARM shipments at over 30 billion chips per year. Nothing else comes close. Even the world's fastest supercomputer, Japan's Fugaku, ran entirely on ARM. Not x86. ARM-based Fujitsu A64FX chips delivered 440 petaflops, claiming the top spot for years. Backward compatibility kept x86 dominant for decades. A program compiled in 1995 still runs on a 2024 Intel chip. That's a powerful selling point. ARM doesn't carry that legacy weight. Each new ARM generation can break things. But it can also redesign things. Move faster. Adopt new technology without compromise. The two architectures had reached a balance. x86 ruled desktops and servers. ARM ruled mobile and embedded. Each side seemed comfortable in its lane. Then something shifted dramatically. Here's what changed everything. November 2020. Apple announces the M1 chip. An ARM processor inside a laptop. The MacBook Air. No fans. No throttling. Massive performance. The M1 outperformed Intel's best laptop chips while using a quarter of the power. Benchmarks didn't seem real. The tech press kept rerunning them to confirm. And then, Apple killed Intel inside Macs entirely. Within 2 years, every Mac shipped with ARM-based Apple silicon. A 20-year partnership ended in 24 months. 2023. Qualcomm launches the Snapdragon X Elite. An ARM chip aimed squarely at Windows laptops. Performance matching Intel Core i7 at half the power draw. Microsoft responds aggressively. Windows on ARM finally gets serious investment. The Surface Pro X Copilot Plus PCs. The entire Windows ecosystem starts pivoting toward ARM-native applications natively. Then Nvidia enters. Their Grace data center CPU. ARM-based, paired with their GPUs for AI workloads. Suddenly the most valuable compute platform on Earth runs ARM at its core. And the kicker. Intel's 2023 quarterly losses topped $16 billion. Their fab business hemorrhaging cash. The x86 monopoly that defined computing was visibly cracking. Meanwhile, ARM Holdings went public again in 2023. Valuation, $60 billion. By 2024 it crossed $150 billion. The licensing model finally paid off massively. The numbers told the story. ARM chips were now 80% of all processors shipped worldwide. x86 was technically still dominant in revenue, but in volume. Crushed. So what really happened? The lesson is about efficiency. For decades, performance meant more transistors, more complexity, more power. ARM proved a simpler design could scale farther. Mobile computing was the catalyst. When the battery became king, what's mattered more than gigahertz? ARM was built from day one for that constraint. x86 had to retrofit. Then artificial intelligence accelerated the shift. AI workloads care about throughput and energy. Data centers care about the electricity bill. ARM's efficiency advantage became money saved at scale. It also matters that ARM doesn't compete with its own customers. Apple, Qualcomm, Amazon design unique chips on top of ARM's blueprint. Innovation happens on many fronts simultaneously. x86 still has clear strengths. Single-thread peak performance, mature software ecosystem, decades of compiler optimization tooling. Gamers, workstation users, and many enterprise apps still strongly favor it. But the trend is clear. ARM is growing fast. x86 is defending territory. The next decade will likely see ARM dominate both edges of computing, the smallest devices and the largest data centers. There's also a third player rising. RISC-V, open source. Royalty-free. Designed in academia. It could one day disrupt both ARM and x86. But that's a video for another day. The takeaway is this: architecture choices made in 1978 and 1983 still shape the device in your hand right now. Decisions matter. Designs persist. If this changed how you see your devices, subscribe for more deep dives. Comment with which chip powers your daily computer.